Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we are going to show another theorem. We're going to be providing proof of another theorem. This is the theorem that we would like to show. So in this case, we have a random sample of n normal random variables. Okay, they are IID, meaning independent and identically distributed, right? And with them, they are standard normals. Okay, meaning that they have mean 0 and variance 1. So now, with these guys, we create a new random variable, v. This transformation is defined as follows. It's just going to be the sum of the squares of our n original random variables. Okay? So what we would like to show is that v has a chi-square distribution with n degrees of freedom, or something that is equivalent. We would like to show that v has a gamma distribution with parameters alpha n divided by 2 and beta 2. Okay, so let's do that. Okay, let's show this, and just like we showed that other result, theorem 7.1, right, and we used the MGF approach. Again, we're going to be using that same approach to show this result. Okay, here we go. So first, by definition, the MGF of our random variable of interest, that transformation v, is just the expected value of e to the power t times v. Okay? Now remember that v is going to be the sum of the squares of those n standard normals. Okay, so let me plug in here v stands for C1 squared plus C2 squared and so on, right? Dot dot dot, we have n of them and standard normals that we squared. Sense? Okay. Now, this is the same. Let's do a little bit of algebra on that exponent. This is the same as this, right? T times C1 square, T times C2 square, T times Zn squared. Okay? Now, this is the same. It's just a product of exponentials, right? Let me just write this down here, copy this guy here. Let me put another one here. Okay. You guys agree? So expected value of e to the power t times c1 squared plus t times c2 squared plus dot 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 t z n squared is the same as this. Expected value of this product of exponentials, right? Now, we know that these guys are IID, independent and identically distributed, but the important part here for us is the independence. Since they are independent, the expected value of the product is the product of expected values. So we get to rewrite this like this, right? Now that will be very useful, because if you take a look at this, at that expression, that is just by definition the moment generating function of z1 squared. So let me write that down, okay? This is the MGF of z1 squared evaluated at t. And then this guy is going to be the MGF of z2 squared. And so on. Last one is going to be the MGF of Zn squared. Now they are identically distributed. They have the same distribution. And we also know that, and let me remind you about that, recall that the distribution of z1 squared, or we could say ci squared, any of those guys, is going to be a chi-square with 1 degree of freedom, right? So that's going to be useful as well. Let me find that chi. Where do we have chi? There we are. Chi squared with 1 degree of freedom. Okay? So let's refer to our table, and then the MGF of z1 squared is going to be the MGF of a chi squared with 1 degree of freedom. Chi square, there we are. So this is a chi square with new degrees of freedom, so we just have to plug in a 1 here, so it would be 1 minus 2 times t to the power minus 1 divided by 2. Okay? So from our table, what we have is 1 minus 2 times t to the power minus 1/2. And then we have the same for the second one and for the third one, and so on. We have n of them, right? So now we just do a little bit of algebra. We add them up, so we have n of these terms. So what we end up having is 1 minus 2 times t to the power minus n divided by 2. Okay? Now, if we go back to that table of ours, right, we will realize that, guess what? That's the MGF of a chi square with n degrees of freedom. Okay? So by by the uniqueness property of MGFs, we have that V has a chi-square distribution with degrees of freedom n, right? Or in other words, if you take a look at the MGF of a gamma, right, you can see that what we have, we could rewrite that, we could express that as, hey, the MGF that we are dealing with is the MGF of a gamma with parameters alpha equals n divided by 2, beta equals 2, which is just equivalent. Make sense? Can you see it? This is the MGF of a gamma random variable with beta equals 2, alpha n divided by n. That would be another way of saying it. It's equivalent. Okay? So, let's summarize what we did here. So using the MGF approach, we showed that if you create that transformation, the sum of the squares of n standard normals that are independent, then the distribution of that transformation, we're calling it V, the distribution of V will be a chi-square with n degrees of freedom, or equivalently, the distribution of V is going to be a gamma with parameters alpha n divided by 2 and beta 2. Okay? Well, that's it for now. Thank you so much. Please take care and keep working hard. See you next time. Bye.